All right, everyone. Hello. Sorry for the delay. Welcome, everyone, to the free webinar series presented by WePast. My name is Christina Ruiz, and I will be your moderator today. Throughout the webinar, we will stop the presentation to review. There will be multiple choice poll questions which will be available to answer in the sidebar. Please go ahead and answer these questions as they come up. And during the webinar, please feel free to use the chat window to ask questions on the topic, since we'll take time during the presentation to answer these. And this and other recorded webinars will be available to WePast subscribers. You can register through WePast.com to become a subscriber. Today's topic is dose calculation algorithms in teleradiotherapy, presented by Michael Fix, PhD, and a deputy head of Division of Medical Radiation Physics at the University Hospital Bern in Switzerland. Thank you for joining us, Michael.
You're welcome. Thank you for the invitation I received from David, and I have heard that this is the first intercontinental webinar, and it's also my first webinar, by the way. So I would start with an overview about topics which I would cover in this webinar. I will start with an introduction, followed by some basic radiation physics thoughts which are needed for preparing the dose calculation algorithms. Then I go through correction-based algorithms, followed by model-based algorithms, and giving a short summary and some references to this topic. So I will start with the introduction, and I will start from a very general point of view that a treatment planning system for a head and neck VMAT case. What is what we expect from a treatment planning system? Of course, we would expect having some treatment field properties, that it calculates the dose distribution in gray and provides us with evaluation tools, isodose levels, color wash, DVH, etc., looking something like this. But actually, that's not the most important point. One of the most important points of the treatment planning system is also to provide us with the monitor units to be set on the LINAC. So there is a connection between the dose calculation algorithm and the local LINAC. And that's what's need to be part in the dose calculation algorithm. So when we do want to come up with a dose calculation algorithm, it's worthwhile to think what kind of physics do we need to take into account for doing this? What kind of physical interactions does have an impact on the dose distribution? How does it affect the primary and scatter contribution? And this depends on, and this is an example, on the cross-section data and on the energy range we are looking for. Whether this is for KEV, diagnostic energies, or whether this is in the therapy range where the Compton effect, for example, is predominant. The Compton effect is also something we see in the dose distribution, and I made an example here. For the depth dose, the build-up region shown here for different energies. This is the visualization of the Compton effect, releasing electrons at the surface, but they have enough energy to prolong in depth, giving us the build-up of the depth dose curves. But this effect is not just visible in the beam direction, also laterally. And this is shown by the following graph, showing here for the depth dose curves for a large field size, and it's containing also graphs for very small field size. This is the lowest field size for a circular field of 0.5 centimeters. And we see that laterally there is still not the equilibrium reached, and it's going to increase for increasing field size until we get a saturation. In all of them, we see the build-up in the beam direction. So what kind of distances we are talking here about? That depends whether we go in beam direction or laterally, and it also depends on the energy. While in water for a very low energy, the depth of equilibrium, it's a few millimeter, and the lateral equilibrium, it's almost not present. If we go to 1 MeV photon energy, there is also already a couple of millimeters build up, and laterally 1.5 millimeter. We see on this graph that for increasing energy, the build up laterally as well as in depth is increasing, and that the lateral equilibrium is shorter in dimension due to scatter processes than in the depth dose region. So now continuing to the impact of the dose on tissue in radiotherapy, which is shown in the dose-response relationship, showing here. And this gives us some estimation of how accurate such a dose calculation should be, actually. So these are the tumor control probability as a function of dose, along with the normal tissue complication probability. And if we now look at the, at a dose of 54 gray, for example, we get a probability of 80% to control the tumor. Now, if this dose delivery is associated with an uncertainty of plus minus 5%, it turns out that the steepness of this tumor control probability ends up with an uncertainty of 25% in the control rate. So a rather small uncertainty at the dose delivery results in a tremendous uncertainty in outcome or tumor control. It's even worse for the complication probability in this case, where we have an uncertainty of 30%. So this rises the level of accuracy we should achieve with dose calculation algorithms. So after covering now the basic principle in radiotherapy in terms of accuracy and in terms of basic physics quantities we should take into account in the dose calculation algorithms, we can proceed in saying how actually can we calculate the dose. And in principle, we can say that the transport equations for photon and electron fluences are known, that the equation, the relation of dose to electron fluence is given, because principally all cross-sections are known from theory. But on the other hand, it turns out that this gives results in a couple of differential equations for given geometry and boundary conditions. And those are hard to solve, and typically only numerical approaches like a Boltzmann solver or Monte Carlo simulations are appropriate. So people have been coming up with much simpler, with including approximations in order to calculate the dose efficiently. And typically one distinguishes between so-called correction-based dose calculation algorithms or type A calculation algorithms. And those are built by calculation based on measurements in water. You have to do a lot of measurements in water for your local linear accelerator. In the second step, you then make a dose calculation within water and apply correction factors for getting an estimate of the dose distribution within the patient. So that's why they are called correction-based dose calculation algorithm. A second type of algorithms are called model-based dose calculation, and those are calculation algorithms which are directly calculate the dose in the patient representation, while the correction-based have applied these corrections independently, for example, for field size and surface irregularities as well as inhomogeneities. The model-based dose calculation algorithms apply the dose calculation directly in the patient's representation. Also, the monitor units are calculated by beam intensities and not by dose in water. So there is a direct relation between the beam intensities and the MU calculation, which in turn then make an explicit B model necessary. So in the first part, I would go through the correction-based dose calculation algorithm. And if we look a little bit more in detail, we have an approximative B model and in place. And this is represented by a tremendous amount of initial measurements in water. Typically, it's done by depth dose curves, dose profiles. We need to have an absolute reference dose. That's where the link from the dose calculation algorithm to the treatment planning system comes along with. And of course, we need somehow to cover all the dependencies of the dose distribution given by field size, depth, source to surface distance, energy, etc. If we have done all these initial measurements in water, we need to come up with lookup tables and parameterization in order to calculate the dose within the water system for a field shape given by the patient-specific situation. Also in this, and we will see that there is the method of separation between primary and scatter contribution. So we have this separation not only for the model-based dose calculation algorithms, but also for these more simple correction-based algorithms. Finally, we need to apply these corrections for getting an estimate of the dose calculation in the patient. And I will go through all these three topics in the next slides. So first of all, there is a representation in the percent depth dose curve, which probably everybody knows. So this is a water phantom with a certain source to surface distance. We have the point P in the depth of dose maximum and the point Q for a given field size at the surface. And the percentage depth dose curve, it's a function of depth, the field size, the source to surface distance, as well as the energy. It gives the ratio of the dose at the point Q divided by the dose at the point P. These can be also expressed as a ratio of dose rates. The 100 is just to get the percentage. Now to characterize those, that if we keep all these three, the depth, the focus to surface distance and the energy constant, the percentage depth dose will increase with increasing field size. This is due to the fact of increased scatter volume. If we change the focus to surface distance, the percentage depth dose will increase as well. And this is due to the fact that for increased distances, the impact of the inverse square law is decreasing. Finally, if we change the energy and increase the beam energy, the PDD is again rising due to the increased penetration of higher energy photons. So this brings me now to the quiz question 1. And there the question is, which of the following 5 statements is false? First is PDDs are used to characterize the dose distribution of a linear accelerator. There is no explicit B model for correction-based dose calculation algorithms. PDDs depend on beam energy, depth, field size, and source-to-surface distance. The dose calculation algorithm is linked to the linear accelerator, and the accuracy of the dose delivery within 5% leads to small changes in outcome.
Okay, great. So we'll give everyone just about a moment to weigh in on that poll question. And in the meantime, we've got a question here in the chat, Michael, which I think we can address from David. He asks, what algorithms take into account of pair productions? Are they needed at all?
This depends a little bit on the beam energy you are looking at. Typically nowadays, many use only 6 MV photon beams, and there the pair production is not that relevant. But still, there are machines out using 18 MV for Varian machines, or even higher energy for Siemens, where the pair production needs to be taken into account. For these correction-based algorithms, this is intrinsically the case because in the measurement, all the physics interactions are already accounted for. It's within the measurement, so they would take this into account. Explicitly, they are used in Monte Carlo simulations where you potentially could switch them off.
All right, great. Looks like we've got one more question that just came in that we can address before we move on. What algorithm takes into account neuron production containment at high energy?
Those, to my knowledge, are only taken into account by Monte Carlo simulations, where you can simulate the interaction of nuclear processes explicitly, and so you can simulate the generation of neutrons. Typically, the contamination it's at a very, very low level, so you need to look at the 1% level of accuracy to, or even below, if you want to take them into account.
Okay, thank you. We can get back to our poll. Hopefully everyone had a chance to weigh in. Could you go over the answer?
Oh, yes. Okay. The majority have hit the right answer. It's the accuracy of the dose delivery within 5% leads to small change in outcome. We have seen that already a plus minus 5% could change it at a 25% level, which is not really small. Okay, now I would like to introduce a second parameter. We are still in the parameterization of the measurements in water for the correction-based algorithm, and this is called tissue-air ratio. So we have here on the left-hand side the situation of the water with a certain SSD distance at a certain depth, in which the field size is specified. We have a point Q, and on the right-hand side we have the similar geometry, but not in water, but just in air. So the tissue-air ratio, it's then defined as the dose ratio in the point Q in water divided by the same point measurement in air. Again, you can do the same ratio in the dose rate domain. So what we can see here is that the tissue-air ratio is not anymore dependent on the source-to-surface distance. So if this distance is changed, it changes in both geometries, canceling the inverse square law out. So it's not dependent on the source-to-surface distance. There is only a small change in the scatter volume, but if the change in SSD it's not that extensive, there is this assumption is still valid. So the tissue-air ratio does virtually not depend on the distance to the source. And this is then making advantage out of, we see in an example in a few minutes. So first of all, I would show you some tissue-air ratio tables and the dependencies. So again, the tissue-air ratio, it's decreasing with increasing set. This is just because the PDD, a part of attenuation, it's still processed to the tissue-air ratio, not the inverse square law, but the attenuation. The tissue-air ratio is increasing with increasing field size. This is again due to the increased volume of scatter. And finally, we have also the beam energy, where similar to the PDD, also the tissue-air ratio is increasing. So now I would come to an example to show why it's an advantage for certain situations to have such tissue-air ratio tables available, and why the most correction-based algorithm use this tissue-air ratio for estimation of the dose in water. And this is the example. So here would be a cobalt source positioned in air with a certain source-to-axis distance. We have here a point X prime, where we provide a certain dose rate of the machine, and this is the object to be irradiated, and we have first a field size of 100 square centimeter here in a source-to-surface distance given by this distance here. And we apply a second field on a rotated phantom or patient, which is the same as if we rotate the beam. In the second situation, we apply the same field size, but we have a different source-to-surface distance for the second case. So if we now have a dose at X prime of 1 gray, we ask what is the dose contribution in the point X for one beam and the second beam to end up with a summed dose of this situation. So we start first to determine the dose X, starting from the dose in X prime, using the tissue-air ratio for the depth, for the field size, and for the energy. So in this case, we have a depth of 10 centimeter, which goes from the surface to this point. That's the distance D. We have a field size of 100 square centimeter. We have a cobalt source. And if we go to the table, it let us know that the tissue area ratio is 0.708. So the dose X, given in a dose X prime, it's 1 gray, we receive 0.708 gray from this beam direction. If we now rotate the patient or similarly the beam, we end up in a different depth, D1 here, which is only 6 centimeter in this case. And so we have to look for the tissue area ratio with a depth of 6 centimeter. The field size is the same, the source is the same. We can use the same tissue area ratio table. This time it provides us a slightly higher amount, which 0.867, leading us to a dose in X at this, from this beam to 0.867 gray. So by this we can calculate the dose from different directions with the same table, which is not the case if we would have used percentage depth dose curves, because there is a dependence of the source to skin distance. So this allows the calculation from many directions, or if we sum this up fine enough, that we can approximate arc treatments by this simple dose calculation using these tissue area ratio parametrization. So this brings me up to the second question of the quiz. Again, I ask which statement is false. So tissue area ratio depends on the field size. Tissue area ratio depends on the source to surface distance. Tissue area ratio is useful for isocentric treatments. Tissue area ratio increases with beam energy, or tissue area ratio decreases with depth.
Great. So the poll is up and live for anyone that wants to weigh in. You can just go ahead and click on the sidebar, the question, and we'll go over the response in just a minute. And if anyone else has any questions they'd like to ask in the chat room, we just want to remind everyone that that's available. You can post your questions and we'll take a moment to go over them so that Michael can answer those questions before the end of the webinar. So we'll just take a few more moments here to let everyone weigh in on the poll, and then we can turn it over to you. It looks like most people are getting the answer, though. Michael,
yes.
Maybe you want to just go ahead and answer it.
That was a rather easy one, I think. I just emphasized this so much. That's the right answer is the tissue area ratio depends on the source to surface distance. This is not right. The tissue area ratio does not depend, and that's why it's so useful for isocentric treatments. So another parameter which has a special meaning, it's the so-called peak scatter factor. And this is just the tissue area ratio defined at the depth of dose maximum. So that's in the depth set max. And then again, it's divided by the dose at point P in water divided by the dose at point P in air. And this provides some special features. One of those is that it's dependent on the field size. And if you provide a scatter factor as a ratio of this peak scatter factor, putting in relation the peak scatter factor of a certain field A to the reference field of a 10 by 10 field, we get the scatter factor, and that's taken into account the phantom scatter. Some are also calling this phantom scatter factor SP. That's the nomenclature used typically by Kahn. That should not be mixed with a scatter factor due to collimator scatter, which is in Kahn's notation as C. And this is divided by the dose in air at a certain field size divided by the dose again in air to the reference field size of a 10 by 10 field. So this takes into account the collimator scatter as well as potentially a backscatter into the monitor unit, while this here just takes into account the phantom scatter in the scatter volume of the water. This is due to the fact that the collimator scatter in each peak scatter factor is cancelled out due to this ratio up here. So that provides a method to separate phantom scatter from collimator scatter. This leads to another relevant quantity, which I think most of you are aware of. This is called the relative dose factor, RDF, or in Cancer notation, the output factors. And those are dependent on collimator scatter as well as phantom scatter. And this relative dose factor is defined as the ratio of the dose in water at a certain field, at set max, with a certain field size divided by the dose, again in water, at a reference field size of 10. And in Cancer notation, this is just the product of the collimator scatter as well as the phantom scatter. So this slide here shows an example of the functional dependence of the output factor. Obviously, it's normalized at the 10 by 10 field. It's made to be normalized to 1. So at the 10 by 10 field here, we get an output factor of 1. And this is the typical shape we expect for the output factor. If we increase the field size, the phantom scatter as well as the collimator scatter gives a rise in the dose at the same point in water. And if we decrease the field size, the output factor drops. And it drops, the decrease, it's more emphasized the smaller the field size gets. So those factors I have discussed, the PDD as well as tissue air ratio as well as the peak scatter factor, they are not independent, obviously. They are related to each other, and I found this graph very useful to show this. This is the situation in air. This is the one in water, and along this axis, the relation of the points are due to the PDD, the ones at the level of the depth of dose maximum, it's the peak scatter factor. The tissue air ratio, it's at the normal depth. Oops. And the one missing, it's just this one, it's the inverse square law, which happens to link those points just in air where no attenuation is assumed. So those four are related to each other, and if you have 3, you can determine the fourth out of them, and this is shown in this slide. You have the PDD linking these two, and you have the tissue air ratio, the peak scatter factor, and now you can do a little math and get all together and link the tissue air ratio with the peak scatter factor, with the PDD and the inverse square law. So if you have this tissue air ratio, you can go with the inverse, the peak scatter factor and the PDD down, and then it gives the tissue air ratio. So it's not really a surprise that those 3 quantities exactly show up here with the peak scatter factor, PDD, and inverse square law. With this, you can determine and replace 1 out of the 4 quantities. This is also a method how you can determine PDDs out of the tissue air ratio, or how you can determine PDDs when the source to surface distance F is changed. And this is shown here. This could happen in 2 ways. The first way is that the distance change while keeping the field size at the surface at the same. This is just the formula from the last slide. Now, if you do this, you have the same peak scatter factor for both situations. So the ratio of these PDDs for different source to surface distances will not depend on the peak scatter factor anymore. It's just the ratio of the tissue air ratio for these different field sizes. As a consequence, the field size here gonna change due to the change of the source to surface distance. And you have the ratio of the inverse square law. On the other hand, you can also have a change in the source surface distance by keeping the field size at the level of the depth of where the point Q is located the same. In this situation, the tissue air ratio, it's going to be the same, it will cancel out, but the peak scatter factor has a change in the field size on the surface, so this will remain seated in the formula, and the ratio of the PTDs, now with different field size as well as different source to surface distances, will depend on the ratio of the peak scatter factor as well as on the change in the inverse square law. Now I have talked a lot about tissue air ratio. If we have an increased energy, then it's going to be very difficult to apply measurements in air. You need to have a charged particle equilibrium, and you need to use build-up caps, and they get rather huge for high beam energies. So what you do is that you change the reference media from air to water. So if this is the situation in water you have had before, it's not going to be put in relation to air. It's more related to a water situation where you have a specified reference depth. And if this reference depth is the dose maximum, then you are talking about tissue maximum ratio. So this would be tissue phantom ratio, this would be tissue maximum ratio. However, all the dependencies and relations I have discussed for the tissue air ratio are also true for the tissue phantom ratio. So the formalism does not change with this respect. So now we have a parametrization of the water measurements by typically using tissue air ratio or tissue phantom ratio. And now we need to think of how to apply those quantities for different field size. Typically, a patient has a patient-specific field size, and we need now to take this into account. And first of all, we can use the transformation from rectangular field sizes to square field sizes and circular field sizes. So we start with a rectangular field size, and the corresponding equivalent rectangular field size, it's provided by, if A and B are the length of the rectangular field size, the equivalent square field size, it's given by this formula, and this it's determined by keeping the same area to perimeter ratio, and from the square field size to circular field we determine the equivalent radius, and this is the constraint that we want to keep the same area of the two field sizes. But even if we can now switch between circular, rectangular, and square field size, typically we have irregular field sizes formed by MLCs, shown at the LINAC here, or the typical variant image of the MLC shaping an arbitrary irregular field. We need to have a mechanism how we can take those irregular shapes into account. And here is an example of a mantle field. So this is the field which is open for the beam, and around here it's blocked. So this would be the border of the field shape here. And we want to determine the dose distribution along the depth dose of going through the point Q. And for this, it has been determined that now a separation between the primary contribution and the scatter contribution, it's highly appropriate. So one separates the tissue air ratio for a certain depth at a certain field size, that's the radius of a circular field size, into a component which has zero field size, which is nothing else than the primary component, and a so-called scatter-to-air ratio. And of course, the scatter-to-air ratio then keeps the dependence of the depth as well as of the field size in question. So we can, similar to the tissue air ratio, also the scatter air ratio, put into a table, which is shown here for increasing depth and increasing field size. We get for a cobalt source and increasing scatter to air ratio. So with increasing field size in this and increasing depth in this direction, we have an increased scatter contribution. That's what we would also expect due to increasing scatter volume. So now how can we determine these dose distribution or the dose estimation along the PTD at this point given the irregular field? We now separate the field in segments. In this example, we have 36 segments. And for each of these segments, we determine the radius of the field, which is going from the center, from the line, from the axis we want to determine the dose along, to the border of the field size. And for this circular field size, for this segment of the circular field, we determine the scatter or air ratio contribution to this axis point. And of course, this is only 1/n segment. And this now has to be done for all segments. So for the first, second, third, fourth, and so forth. And the segment 7 here, it's somehow special as it has a contribution from this open field part. This part is blocked and this is open again. So we need to have a scatter contribution, which is a superposition of the involved segments going from the center to this border, to the second border, and the most outest border. And this is done as shown here. We first start with the most off-axis contribution of the scatter. We subtract the next part, which is going from the center to this part. So now we underestimate the scatter because we have another contribution from this part, which is added at the third term. By doing this for all n segments, we can determine an average scatter to air ratio and then plug this in the tissue air ratio for the depth set at the irregular field as a contribution from the primary contribution and this averaged over these segments of the scatter air ratio. And then finally use the previously presented formula of how the tissue air ratio is related with a PTD by looking at the peak scatter factor and the according inverse square law. This method is called the Clarkson method. So this allows, with this simple correction-based algorithm for arbitrary field size, to determine the depth dose curve along an axis. So this pops up now the third quiz question. This time I want to look for the statement which is true. So the first answer would be the Clarkson method is used to determine monoenergetic dose kernels. The Clarkson method is used for dose calculation of seed therapies. The Clarkson method is only suitable for calculating the dose on the central axis. The Clarkson method can be used for convex and concave treatment fields. The Clarkson method separates primary and scatter components of rectangular fields.
Okay, thank you, Michael. So while that question is up, we've got a couple questions here in the chat, which I was hoping we could answer. Some of them go back to the TAR method. You'll see here it says, up to what energy TAR method is useful?
You find them still for 6 MV, but this is kind of a borderline where many calculations switch to tissue maximum ratio or tissue tissue phantom ratio.
Okay. And then we have one more question, which is not public, but it's private. Is TAR good up to 3 MV?
3 MeV, which would be Yeah, it's showing 3 MeV, which would be monoenergetic. This is borderline. In a 6 MeV beam, the spectral contribution of 3 MeV, it's rather small, so that would be still fine. But the range of secondary electrons of 3 MeV would already be 1.5 centimeter in water, which is already kind of a big build-up cap to be used. I once saw a build-up cap for an 80 MeV beam, and this is really huge. This is a couple of centimeter PMMA thick.
Okay, thank you for answering those questions. I think everyone's had a chance to weigh in on the poll, and it looks like some answers are pretty close.
Yes, okay. That's a more tricky question. So the right answer would be that the Clarkson method can be used for convex and concave treatment fields. That's you can have really irregular shaped ones, and the mantle field has convex parts as well as concave parts. Many have also mentioned that the Clarkson method separates primary and scatter components of rectangular field. Actually, it's used for circular fields. So these contributions are always determined from circular fields and not from rectangular fields. That would be more tricky if you think of going close to the corner of the rectangular fields, especially if you have elongated rectangular fields. Circular fields are, with this respect, less sensitive. Okay, now where are we in the list? We have looked at the initial measured data in water. We have made lookup tables like the tissue air ratio or tissue phantom ratio. And now we need to apply correction for the dose calculation in the patient. So the first one would be that we need to correct for surface contours and oblique beam incidence. I look into the surface contours. So we don't have this plane surface like we have in the water phantom also for the patient. And there are two potential methods which are used for correcting this. The one is the effective SSD method, and the other one is the tissue air ratio, tissue maximum ratio method. And a second correction has to be applied for the inhomogeneities. And as mentioned already before, all these corrections, whether this is for the field size, for the surface contours, or the inhomogeneities, are independent from each other. This is not the case for model-based algorithms. So looking at the effective SSD method, if we have this situation where the surface is irregular and we assume we are at this level with our PDD at this location, we want to calculate what is the dose at this point, as given we have the PDD at this line. So we need to apply a correction, and this would be the dose in the depth set. So this would have the right depth set, but this is still assumed that the PDD starts at C double prime. So it would be starting from here, going to the depth set. What this method is doing, it's shifting the depth dose to this location. So it would account for the right attenuation and the right depth. But giving the shift from C double prime to C prime would mean that the inverse square law, it's not considered yet. So this is why there is an additional correction of taking into account this difference in the inverse square law exactly by this distance h from here to here. So that would be provide the appropriate correction. So that would be the corrected PDD at this location. Alternatively, you can use the tissue air method, tissue air ratio method, and this is taking the PDD double prime with the starting from the C double prime to the point set as in question. So it uses set plus h. So that would be the right inverse square law, but it would overestimate the attenuation because the depth would be too large. There is still an amount of air available where the attenuation does not take place. And since the tissue air ratio just corrects for the attenuation, but it's independent of the inverse square law, we can apply the ratio with this difference in depth of tissue air ratios here to get, again, a correction for the PDD. So these are the methods to have irregular surfaces taken into account for the correction-based algorithms. Next would be inhomogeneities, and I make this first with an example. This would be a water phantom with a low density inhomogeneity, and this is the path along. There are several points highlighted, and these points would see a different dose from those they would see if all would be water. And first of all, this E to G would see higher doses due to the decreased attenuation in the low density material. A would see a lower dose due to missing backscatter from the low density area. And B, C, and D depends or difficult. There are opposing effects in point B and D. You have an increase in dose due to less attenuation of the low density area. But on the other hand, you have a decreased contribution due to missing scatter in the low density area. So these are contradicting effects. So you do not know upfront which one it's overcompensate the other one. Point D, it's not in the charged particle equilibrium. That's extremely difficult to determine and typically leads to huge errors for correction-based algorithms. Now, what kind of correction we can apply for this inhomogeneity? So we have the dose in the inhomogeneity, or taking those into account. It's a correcting factor times the dose we calculated in water. And there you can have the path length correction method, tissue air ratio correction. Many might know the Bartho correction or the equivalent tissue air ratio correction. I go quickly through those four. The first, I made an example. We have here at the point C, which is 1.5 centimeter until the inhomogeneity begins. We have 2.5 centimeter within the inhomogeneity, and the depth Z prime, it's now weighted with the density. So the first part, it's unaffected because the density is 1, and then it's 2.5 centimeter times the low density, which gives a value of 2.125. So the correction factor now, it's the ratio of the PDDs at these different depths. So that would be the original depth, that would be the modified path length corrected depth. And so this is shifted higher because this would be 4 centimeter. This is only 2.125 centimeter. And thus we would correct the attenuation, but we would again be shifting this point backwards, so to speak, which would lead to a wrong inverse square law. So we need to correct with the inverse square law for this. However, there are still some problems with this correction. One is that point A is not affected at all. So up to here, we would still get the same PDD. But as mentioned, this dose would be lower due to missing backscatter. B and G, so all those points would not see any effect of this lateral contribution of or impact to the dose on the central axis. So what this correction factor is doing, it corrects the primary part of this depth dose contribution, but it does not account for the impact on scatter. And as mentioned already, there is a decrease due to the missing attenuation, but there would be there is an increase due to missing attenuation, but there would be a decrease to scatter. So overall, what this path length correction does, in this case, it would overestimate the dose because the reduction due to missing scatter would not be taken into account. So the second one, it's illustrated in this sketch. You have a layer of water and a layer of heterogeneity and water again, and you are interested in this point P. They have different thicknesses of the layer, and the tissue air ratio correction, it's now very similar to the PDD correction. It's the ratio of the tissue air ratio by different depths. The one it's taken into account similar to the path length correction, but this time with the electron density. And this is the original depth, so it corrects the attenuation properly, and it's not dependent on the source to surface distance in this respect. It still does not look at the distance to the inhomogeneity. So as you can imagine, if this point is very close to the inhomogeneity, it's affected more than it's further away. And this is typically taken into account in the batho correction, where you explicitly look at the tissue air ratio at this distance Z3, which is the distance from the point to the above considered inhomogeneity. And finally, the most complex correction method, it's this equivalent tissue air ratio correction, where you look at this, you take into account the attenuation by the different depth of the tissue air ratio, but you also change the field size, and the field size is changed such that you would like to generate the same scatter condition in this point P. And how is this done? This is again the radius of the circular field. As an example, you weight this with a rho tilde, and the rho tilde, it's the sum of the densities you receive from the CT. You score it through the whole CT and provide a certain weight, which can be interpreted as the contribution of this voxel in terms of scatter to this point P. As you can imagine, you need to do this for each point P you want to calculate the dose, and always you have to go through the whole 3D CT data set, which is rather computational expensive. So I'm already at the quiz question number 4. And which correction method does not work? The effective SSD method is used for correcting surface contours. The tissue air ratio method is used to correcting surface contours. The equivalent path length correction is used for correcting surface contours. The batho correction is used to correct for heterogeneities. And the equivalent tissue air ratio correction is used to correct for heterogeneities.
All right, so let's give everyone a moment to answer this poll on the sidebar. And it looks like there's still no new questions in. So if anyone has any questions for Michael, please go ahead and put those into the chat window so that we can answer your questions before the end of the webinar. So let's see how our folks doing. Looks like a lot of people are getting the right answer here. Michael, why don't you go ahead and go over those questions?
Okay, the most picked it right. The equivalent path length correction is used for correcting surface contours would not work. That's just for getting the inhomogeneities right. Okay, now I'm at the end of the correction-based algorithms, and I want to finish with the limitations and the motivation at the same time for the model-based algorithm. It's required a lot of dose measurements. It's always assuming electronic equilibrium, and this results in large errors near heterogeneities. And that's why there is a more complex or type B model-based dose calculation in place, which directly calculates the dose in the patient representation. Examples of those model-based are the convolution superposition algorithms, and in this definition also the Monte Carlo simulations are type B algorithms. I will cover a little bit about the convolution superposition algorithm, and in the next week's webinar I will focus on the Monte Carlo simulation. So the model-based dose calculation assume that the primary photon releases secondary particles by some physical interactions. We can describe them very precisely, and these secondary particles deposit the energy in the medium. And if we now can assume that this medium is homogeneous, we can pre-calculate the energy deposition by secondary particles as independent of the location of the interaction site. So this plot shows an interaction site, and the released energy in this interaction site leads to this dose distribution shown in this graph. So the energy deposition by secondary particles can be pre-calculated, and this speeds up the computational process substantially. Again, it's a more intrinsically methodology in separating the primary and the scatter components. So in the first, you have the energy deposition by the primary photon interaction. So if we want to determine the dose at this location R, we have a primary component here, and we have many scatter photon interactions at all other places, and this is just one example. At this location, we have a scatter contribution of released energy in point S contributed to a certain scatter dose in point R, and we need to sum this up. If we do this in a very general way, this leads to a superposition of the dose deposition of weighted responses of point interactions. So this is then an integral. At location S, where we release a certain energy, we count for a contribution of this energy release in S towards the point R, where we want to determine the dose. And this is the convolution superposition. This is a convolution of the energy, total energy released at this point S. And this is the dose or energy deposition kernel of what is the contribution in R given the energies released in point S. And we do integration of all potential point S in the volume. So this total released energy per mass, it's typically called terma, and the contribution of the energy released in S to a point R, it's described by the energy deposition kernel. So now we need to know how we can determine the terma and how we receive the kernel in order to apply this convolution to determine the dose. So first to the terma, the total energy released per unit mass. So it's comparable with the kerma, but it's not really the same. It's covering the total attenuation coefficient weighted by the energy fluence, not only the transferred energy to charged particles. This also takes into account the energy of a secondary photon released in this interaction point, for example. So this terma in the point R, that depends on the primary photon fluence, which is sketched here. Typically, the terma is calculated by ray tracing from the source. There is a description of the beam characteristic in terms of energy fluence, and those get ray traced to the calculation volume, and at each point of the calculation volume you determine then this terma T by calculating the energy fluence and weighted it by the linear or mass attenuation coefficient. For this you need to have an explicit beam model describing the energy fluence characteristic of the treatment head, impinging on the volume you want to have to calculate the dose. In this respect, although there heats a water fountain, you can think of the patient's representation. So the surface contours are already at this stage taken appropriately into account by this ray tracing method of the terma, which is different from the calculation-based algorithms. Of course, also the B model generation needs to have a link to the linear accelerator in the clinic, and this is realized by a certain set of measurements which are then defined parameter of the B model during the commissioning phase. So this B model needs to explicitly take into account certain features as the source size. It needs to account for extra focal radiation source due to the flattening filter, secondary collimate, jaws, etc. It needs to look at the beam energy spectrum as a function of off-axis factor, as well as collimator transmission or impact of other beam modifiers. Each of these impact needs to be described, and the more precise and accurate you describe those, the more accurate is your dose estimation in the patient representation afterwards. So errors at this level are propagated as systematic errors in the dose calculation. So going to the kernel, these are typically determined with Monte Carlo simulation. They calculate the energy distribution. You have force and interaction at some location, and then you follow and score the energy deposition like shown in this figure, and then you determine the kernel by relative energy deposition at the distance r from the interaction point divided by the total energy. So this is an example of several dose or energy deposition kernel as a function of energy, and you can see, especially here, different hollows, and those are due to primary to first order scatter and higher order scatter. So you can see these approximations or these separation in orders of scatter. I come to this later on. There are two ways of implementation, and different implementation of commercial dose calculation algorithms are different in this respect. The one, it's the dose point of view. So you loop over the point R where you want to calculate the dose and covers in each of those contribution of all point S. Or you take the interaction point of view where you sit on each interaction point of view and look where, at which R you contribute a certain amount of dose. And this is illustrated in this graphic. This is the dose point of view. You sit here and you calculate all the contributions of all points S in the grid, or you sit at the interaction point of view and distribute to all points in the grid the contribution from this interaction site. Finally, you need to think that we have just spoken so far from one beam energy. You have typically a polyenergetic beam, so you have another integration over the beam energies in the beam. And this gives you then a double integral. And like shown here, the terma, it's a function of the energy fluence of a certain energy weighted by the mass attenuation coefficient for this energy. Now, if inhomogeneities comes into place, this is typically handled with density scaling of the kernel. So I hope you can see this unchanged kernel, which would be applied in a homogeneous situation. It gets stretched to the right due to this low density material. And this is done in the function that the distance between the release of the energy and the deposition dose, it's weighted by the density along the path. And this makes the convolution then to a superposition because the invariance in the spatial domain gets lost. So the final quiz, question 5, which statement for model-based dose calculation algorithm is false? The energy deposition kernel is determined using the tissue erasure concept. Monte Carlo is a numerical and not a model-based approach. Model-based algorithms apply the primary and scatter separation concept. The calculation of the terma accounts for surface irregularities. Density scaling of the kernel accounts for heterogeneities.
Okay, great. So this is our last poll question. So for everyone who's in the chat, please go ahead and make sure to answer this poll question. And we have one question in the chat window, or actually a couple now. Is it mass density or electron density, someone asks?
This typically it's electron density because you assume that Compton effect, it's the most relevant interaction type, and the Compton effect, it's proportional to the electron density.
Okay, and then one more question here in the chat window. Is it the difference between superposition or convolution? Kindly explain a bit.
Typically, the convolution is the part where you have the for one energy, you convolve one kernel, and then you make a superposition over the energy.
Okay, great. Thank you for clarifying that. I think we can head back to the poll. It looks like most people have had a chance to weigh in.
Okay, I didn't check the answer, but the poll itself. But the right answer is the energy deposition kernel is determined using the tissue air ratio concept. This is not gonna work. It's typically Monte Carlo to determine the energy deposition kernel, although one can also use measurements. So after this general description of the convolution superposition algorithm, I want to give two examples. The first one would be the collapse cone algorithm, where you use a point kernel, taking the lateral energy transfer into account, as shown previously. But this time also this point kernel is parameterized, and a separation into primary and scatter contribution as well as electron contamination is taking place. So this energy deposition in the whole space gets collapsed on certain central lines of cones, and this gets then parameterized by this function. So this is along the distance r under a certain angle. And the first term here describes the primary contribution, and the second term describes the scatter contribution. So this is along these lines. And all interaction or all deposited energy within this cone gets deposited along this line. A second, independent from this convolution superposition of the photon contribution, there is another kernel describing the electron contamination. And this is also a kernel which is parameterized by fitting components, alpha, beta, and gamma, due to also Monte Carlo calculations. So this is a separate calculation done, and then the sum of both gives the dose distribution. The approximation is that along this path line, there are at the interaction site, the cone starts and provides the deposition along this line. And what happens that here in this example, if you have the interaction type here along this line, the energy that's deposited of the whole cone. So you would miss the laterally placed energy deposition, but this is covered by the neighboring ray of energy deposition. So these gets exchanged from one cone to the other and vice versa, so makes it very accurate again. However, this accuracy gets decreased for large distances because of the divergence of these cones. It is considered that these errors are small due to the rapid dose fall off of these kernels. So a more simple approximation or a more simple example, it's the pencil beam algorithm, and there the energy deposition kernel, this is the point kernel where the energy is released in a single point, gets integrated over a whole line. So there is a pre-integration over the depth dimension, and this increases the calculation speed. So this would be the point kernel. This gets integrated over the line along the depth, resulting in a pencil beam kernel. So we reduce the whole problem of in terms of one dimension. Of course, in this representation, the inhomogeneities laterally are not taken into account anymore, and this leads to some limitations in accuracy. For the dose calculation itself, not a 3D distribution of the terma is needed, only just the two-dimensional distribution of the energy fluence and the terma it's needed. Again, you have a convolution with the depth, providing you then a 3D dose distribution. one approximation we can see in this picture, that although the surface is differently shaped or the depth is different, the those point estimated in the red location is the same for pencil beam algorithm in all these 3 geometric configurations. With this, I come to the summary of this first webinar. We have seen that accurate dose calculation is important in radiotherapy. Correction-based algorithms are based on many measurements in water. They calculate in a multi-step process first the dose in water and applies independent correction for field size, surface heterogeneities, and inhomogeneities in order to estimate the patient dose distribution. It's a fast calculation, but has some limitations in accuracy. On the other hand side, model-based dose calculation as convolution superposition algorithms, they intrinsically calculate the dose in the patient representation, uses a B model to directly determine the monitor units out of the beam intensities, and thus improve the accuracy compared with correction-based algorithms. The Monte Carlo algorithms provide further improvements, of which we see some of those in the next webinar. So here are some literature, some references, and there are even more references in there, which might be worthwhile to look up and for some further details. With this, I thank you, and we might still have some questions.
We do have one question in the chat here
Okay.
from Jose. Collapsed cone, he asks.
A cone, the cone is a part of the room angle you have in space. You start from the interaction point through a certain area in the room angle, and this defines a cone. These cones are not all shaped the same because the 4 pi room angle cannot be distributed without any holes if you use the same shape of the cone for all of them.
All right, great. Well, if there are no more questions, thank you so much, Jose, for presenting this webinar, and thank you all for joining us for this free event hosted by WePast. I just want to let everyone know that this and other recorded webinars will be available to WePast subscribers, and you can register through WePast.com to become a subscriber. And we've got a little link in the sidebar if you're interested in becoming a WePast subscriber. And be sure to join us for our next free webinar, which is next week with Michael Fix, Photon Dose Calculation and External Beam Radiotherapy Part 2. And that's going to be on Tuesday, April 18th at 1 p.m., so the same time as this webinar. WePast on Facebook, Twitter, and Google+. And if anyone would like to recommend a future speaker, you can contact me directly via email at christina@wepast.com or by taking this short survey. Thank you all again.
Thank you.